Hey guys, this is Srini and you're watching Python tutorials on my channel Python for Microscopists on YouTube. These tutorials are for beginner coders who can be students, researchers, or anyone who's interested in image processing using Python. In today's tutorial, we're going to talk about Scikit-image, one of the libraries in Python that is dedicated to image processing. And let's actually start by looking at the basics. For example, just looking at resizing of images, and then a couple of ways of doing some image processing functions like edge detection, image deconvolution, and finally look at one of the classic use cases from microscopy, which is scratch assay or wound healing analysis. And if you don't know what that means, don't worry, I'm going to explain that in a minute. So instead of a biological problem, we're going to look at it from an image processing point of view. So let's get started. And the IDE that I like to use is Spider. This is part of Anaconda distribution. And I love this because it comes with prepackaged libraries. So I don't have to worry about installing these libraries myself. So let's start by importing or reading an image into Spider. And the way we do that is from Scikit-image import IO. And IO enables me to read images. And by default, I also import from matplotlib import pyplot as PLT. I do this no matter what because I know I want to look at images or data, and this is one way, this is the best way of actually plotting your data. So let's assign a variable for our image, and io.imRead, and our image is located in a folder called images, and it's called test_image.jpg. Okay, and let's in fact read this image as a grayscale image. So the way you do that is as gray equals true. Okay, so this is how you read your images. And now let's directly jump into how to rescale and resize. All of these are within a module called transform in Scikit-image. So from Scikit-image.transform, okay, import. Let's do rescale, and let's do, see, I misspelled this here, transform, F-O-R-M, import rescale, import resize, and also let's do downscaling. Downscale using local mean. And there are many more things that are part of transform. So go ahead and Google search and look at what else you can do with this specific module. So for now, let's actually look at rescaled image. And this is nothing but just do our rescale. That's it. Rescale, and let's rescale our image. And we need to tell by how much, right? I mean, if you look at the arguments here, it takes the image as the first argument, but then you need to say to what scale you want to rescale. You can also do anti-aliasing. If you have a grid and you are rescaling it, you may have these fringes. So to minimize that, you can actually do this anti-aliasing equals to false or true. So let's rescale our image by 4 times, 1.0 divided by 4.0, and then just for the fun of it, anti_, saying equals to true. Okay, so this is it. This is your rescaled image. Now we can just do plt.show, but let's go ahead and run this. So you can see under variable explorer, you can actually see right there, our original image is float 64, 513 by 639. Our rescaled image is 128 by 160. So the image is rescaled. Now pretty much the same thing for resize. Resize equals resize image. Let's resized image equals or resize. Okay, and the arguments are again image and output shape. Again, now we are not rescaling, we are resizing. To what shape do we want to resize? So this can be image and 200 by 200, for example. And you can also do anti-aliasing and everything. So if I run this again, we should see one more here, resized image, and it should be 200 by 200. Okay. And downscale, pretty much the same way. Downscaled image equals downscale using local mean. And again, the arguments are image, the factors, and so on. So let's go ahead and do our image, and by what window? 4 by 3. So this is nothing but it's downscaling using our 4 by 3 block. And within that block, it's actually using the mean value. So when I run this, we should see our downscaled image 129 by 213. And we can visualize all of these images if you want. Let's go ahead and do that for one of these images. .imshow. Let's do downscaled image and go ahead and plot this. And this is our downscaled image. You can see a bit pixelated image right there. Okay. So these are the basic functions within transform module in Scikit-image. So now let's actually go ahead and do something a bit more fun, meaning let's do edge detection and deconvolution, for example. So let's leave our first few lines as is, and instead of test image, let's actually do test image. I think I have one that's called resized or cropped. Test image. Oh, it's under images. So test image cropped. Let's go ahead and use test image cropped. And the reason is I cropped this so we can see these nuclei a bit larger. So when we do edge detection, we can clearly see the definition of the edges. That's the only reason. Okay. And let's do as gray equals to true. And just to see img.shape, this should be a smaller image of 231 by 263 pixels. Okay, so let's okay. There are a few ways of detecting edges. I was thinking about which one to show. Let's just look at 4 or 5 different ways of doing edge detection. So all of these are part of Scikit-image.filters module. So we can do from Scikit-image.filters. We can import. One way is Roberts. Sobel is another one. And if you're in image processing, you know, if you come from image processing background using prepackaged software, for example, Sobel is one of the filters that you may have seen. Shar is one, Privet is another one. Okay, so let's just look at one by one. Edge Roberts equal to as easy as Roberts image. That's it. So looking at your, I mean, doing such a complicated task is literally one line in Python, and that's exactly why I love Scikit-image package. And now we can just look at show edge Roberts. Let's actually look at CMap equals to gray. Okay, otherwise the image appears in weird colors. So let's run this, and you can see how the edges actually look like. In fact, let's go ahead and show just the image to begin with, so you can see how the original image looks like. We can take some time to plot all of these, you know, but I don't want to waste this time typing a lot of code trying to only to arrange all these images side by side. In fact, I can copy and paste. I have a different screen where I've written this, so let me copy and paste that in a second. But this is basically it. This is how you just do edge filtering. In fact, let me copy and paste all the other, you know, detectors, all the other edge functions, if you want to call them, and here they are. Let me delete my plot. And so the other one is edge Sobel. Again, all I'm doing is calling one by one, Sobel, Shar, and Pruitt. And I defined my figure and axes, and I'm actually within to plot it, and then I'm just showing it as 0, 1, 2, 3, and I'm just showing original image, Robert, Sobel, and Shar. In fact, I forgot to include Pruitt, but this is fine. Let's look at these 4 filters or 3 filters side by side, and here it is. At first look, not much difference, but depending on the sample, the type of image, of course, the result is going to be slightly dramatically different, depending on the type of features you have. So this is edge filtering, and in fact, before moving on, I want to show you one of my favorite filters. Let me keep all of this code as is except for the plotting part. And the filter I want to show you, and by the way, if you look at Variable Explorer, Edge, Sobel, Robert, Shaw, and Pruitt, all of these are Float 64, the original image, except they're modified images by applying these individual filters. And again, all of these are part of Scikit-image filters. Now, one other filter that you may have heard of is canny edge detection, or canny edge detector, whatever the name is. You can call it a filter, you can call it an edge detector, but the difference between these and canny is, first of all, this canny is found in skimage.feature module, not filters module. And the output of canny edge is a binary image, and we'll see that in a second. So from skimage.feature, import canny, okay? And again, edge canny equals, that's it. Okay, as easy as this. And actually, when we type this, it should say image and what other arguments does it take. We need to mention sigma, because that is the window that it actually, in a way, sigma controls the amount of, let's say, amount of edge detection. Canny is not just one operation. It does noise reduction. It does gradient calculations. It does edge tracking, among other things that it actually does. So providing sigma, a good sigma, is very useful. So let's go ahead and do sigma equal to 3. Okay, and let's go ahead and show this. plt.imshow, and this is called edge canny. Okay, so now let's, in fact, let's not do all these calculations. Let me go ahead and remove that and run this. So this is how the canny looks like. If I change sigma to 5, for the fun of it, let's just look at sigma equals 5. You can see the amount of edge is kind of going down, and if I do sigma equals to 7, so it leaves even fewer pixels, obviously no pixels now. And if I do sigma equals to 1, I should see a lot more pixels, a lot more edges, which means I have to now deal with some of these pixels, individual pixels within these nuclei. So go ahead and experiment to see which setting works the best for you, okay, for your type of, for your sample. Okay, so this is edge detection, and now let's look at deconvolution. And again, if you are coming from microscopy background, you probably have done deconvolution or on your images. And from a microscopy point of view, what deconvolution does is, at every pixel, I mean, if you look at blurred images in blurred microscope images, especially the blurred light microscope images, there are many reasons why it is blurred, and one of the reasons is the light itself that's actually at that specific spot, instead of being one single pixel or one dot, it actually spreads, right? When you look at the light, when you shine a light onto a wall, you see the bright region, but then you see this halo right around it. So when you're imaging it, that halo also contributes towards your image. But if you know how that halo is formed, then you can take all those pixels and put that intensity back into the pixel where they should belong to. This is what deconvolution is. And this halo, the way it spreads, is called point spread function. You can represent that by using a point spread function. And the reason why you pay money for microscopy software to do deconvolution is because they actually have all the information about the microscope, about the light source and all of that. So they can take this point spread function or calculate the point spread function, or take a pre-known point spread function and perform the deconvolution operation. Obviously, we're not going to do that. We are going to just assign a predefined point spread function and then just look at the result. But the core point here is deconvolution requires the original image and a point spread function, and it calculates the deconvolution. All it's doing is sharpening the image. Okay, for light microscope, it makes absolute sense. So it is actually available under a module called restoration. So from Scikit-image, um, let's go ahead and import the whole thing. Import restoration. Okay, and within restoration, this is actually called deconvolution. So we already are reading an image. So the first thing that we need to define is a point spread function. But I'll show you why we need point spread function in a second. For example, let's call deconvolved image, and then let's just do restoration dot, and there are many ways of doing this. I mean, unsupervised Wiener is one of the algorithms that actually does this image deconvolution. So, and it takes image and it takes a point spread function, PSF. Okay, this is nothing but a matrix of numbers that actually defines why we think the image is blurred. And there is a reason why the image is blurred. And this is the mathematical representation, point spread function, of the reason why the image is blurred. If we know the reason perfectly, then we'll get the best, the sharpest image possible. But in our case, it's obviously going to be an approximation. So point spread function. Now I need to define our point spread function. Now, there are a couple of ways. First, let's just import NumPy, because we know NumPy, with NumPy we can create a matrix of whatever shape and numbers. So I'm going to just define my point spread function is equals to np.ones, okay? And this is going to be 3 by 3 matrix, and I want to divide this by 9, okay? And the reason why I'm dividing this by 9 is I'm creating a 3 by 3 matrix with 9 ones, okay? I don't want to increase the energy of my image, okay? I want to multiply my image by 1, so the image energy remains the same. And the way I want to do that is by normalizing this matrix by dividing it by 9. That's pretty much it, okay? So that's it. So this is how we do deconvolution. And PL, let's go ahead and save this. .im save. And let's save this under images. deconvolved.jpg, and let's save deconvolved, and let's save it as gray. Okay, this is pretty much it. So let's go ahead and run. Invalid syntax somewhere, so cmap, I forgot to type equals. Let's go ahead and run this again, and it worked okay. And hopefully we should see an additional image called deconvolved.jpg right there. So by the way, we are actually still working on test image cropped.jpg, which is our original image, test image cropped right there, and our deconvolved image right here. In fact, I should have used this blurred image, which I artificially blurred. So it kind of looks a bit sharp. I don't know if you can see it, right around here. So this is again one way of doing this. And point spread function, you can get very fancy when it comes to point spread function. In fact, I Google searched in terms of how to create a matrix of a Gaussian kernel. So I can actually create a Gaussian kernel. And I just copied and pasted this, and I can actually use this as for example, as a point spread function. And in this example, the way that it's working is the Gaussian kernel 5 and 1, with 1 being the sigma and 5 is the size of this, length of this. So this is a 5 by 5 matrix. And the total numbers are adding up to apparently 273. So it's normalized by 273. Right here. So this is so let me go ahead and copy this as is, and I would change this a little bit. So let me copy the one that I have from my text here. I edited this a little bit, and let's go ahead and do this. Okay, I defined a kernel, and kernel np. We need our import NumPy. so there you go, and hopefully, and ST, we are using the normalization, normal distribution here, so which is part of the statistics package in SciPy. So I'm going to import scipy.stat or stats, yeah, stats as ST. Okay, so that should be fine. So all I'm doing is 5 by 5 matrix, and it's using, so I defined this as a function, so I'm calling this function with parameters 5 and 3, and let's go ahead and run this, and that's not bad, that's pretty fast. And if I open my deconvolved, and here is the deconvolved result right there. Okay, so anyway, so this is deconvolution. I'm not sure how useful this is going to be for you, because especially if you plan on applying this on light microscope images. But if you can actually get this point spread function figured out for light microscopes, then you know how to do it now. Okay, so finally, let's look at a real world scenario. Let me clean the slate here, and let's start from scratch. And this real world scenario is scratch assay analysis, and or wound healing assay. For non-biologists, what it does is, in fact, I searched for this already, and here it is. So a glass slide with a whole bunch of cells, and you would artificially create a scratch. So here on both sides, what you see is a bunch of cells, and this is the scratched area. And now we are going to image the same sample every few hours and see how the gap gets closed, because the cells proliferate. You can say cells migrate and grow, that's a different argument, are the cells growing or the cells migrating, but the scratch or the wound is healing. So if I scroll down, you can see here, this is the scratch to begin with, and then it narrows, and then finally it narrows it down to this level, and then you plot the area of the scratched region as a function of time. This kind of tells you the healing rate. This sounds like a simple thing, but then this can be a very manual task, if you're using prepackaged software. So let's look at how we can do this, okay? Using the skills that we have until now. So the skills we have is Scikit-image, we have NumPy. I'm not going to talk about OpenCV or anything else. So just using this. So again, by default, the first thing I always import is MATLAB matplotlib.pyplot as plt. Okay. Sometimes I say from matplotlib import pyplot as plt. It's exactly the same, no difference. Okay. And from Scikit-image, I want to import IO. This is how I open. I read images. Sorry, I got distracted by, again, a phone call on the side, but it's on mute. So let's continue. So from Scikit-image, import IO, and let's also import the module restoration, because I know it has a filter that I potentially want to use. Okay, and let's start with this and see where we get. Now the filters, actually, if you, I'm looking at a Scikit-image page, and I'm trying to see which filters to use. So let me go ahead and in fact copy that, and let's open this so you can see exactly what I'm seeing on right here. So when you go to Scikit-image examples, there are a whole bunch of examples right there, and this is a great place to look at for example, edges. You have canny edge detector. Go ahead and practice that, which we already covered here. And right here, they have an example for example, entropy, filtering and restoration. They have mean filters. You have image deconvolution. Again, this is the example that I have used earlier. Entropy is another example right here. And again, it talks all about what entropy is and all of that. But I want to put that in perspective from a image analysis, microscope image analysis point of view. This is exactly what I'm going to use. And where is this available? That's exactly what I was trying to cheat here. It's available under Scikit-image, filters, and rank. There is no way I remember all of these, so I have to cheat a little bit. Okay, so let's go ahead and do that. From Scikit-image dot filters rank, yeah, import. And why am I importing entropy filter? Well, this is the filter again. Do I still have the page open? This is the filter that actually entropy. I mean, if you have physics background, you know this is the amount of disorder in your data. So by looking at this image, the scratch image, you can clearly see that the clean area is flat, not much disorder. This rough area has a lot of disorder. So entropy is one way of quantifying what the disorder is. So I'm hoping to use that as a segmentation tool for this image. That's pretty much it. That's why I looked up for entropy, and then I found this page, and then I realized that entropy function actually uses images and something called disk. You know, you have to define the patch size or disk size to calculate this entropy. So within that disk, it's going to look for entropy. So to do that, they imported skimage.morphology import disk. I'm going to copy, I'm going to go back here and then paste it. Okay, let's remove these empty spaces in case that's bothering you. And from Skimage morphology import disk. And now I just need to calculate entropy. So as long as we are cheating, why not just go ahead and copy that? Entropy is nothing but entropy underscore image. Let me just copy paste it here. By the way, we haven't defined our image yet, so it's not going to work. So my image is equal to io.imread. I should have shown you I already have a scratch image. That doesn't look that great, but that's a real image actually. You can see, let me maximize this. Well, that's not a good way of maximizing. Well, that is a good way of maximizing, except the scale wasn't good. So anyway, so now you can see the flat region versus the cell rich region. Okay, so this is my input image, and the task in this case is to quantify the area of this clean image. You cannot use grayscale histogram-based segmentation here because, I mean, this area has the same mean gray level as the rest of this image. So this is really a tough image processing challenge where you have to use texture filters. Entropy is one of those, you know, to segment these two regions. So let's get back to our code. So now that we understand the problem, I'm going to read this image. And this is under images folder, and I call this scratch.jpg. Okay, so this is it. This is my image, and my entropy image is nothing but entropy image, and disk size, let's start with 3. Okay, I don't know what describe 10 does. Let's go ahead and show so we understand exactly what the implications are. So show entropy image, and let's do CMAP equals to gray. Okay, so let's go ahead and show the image, and entropy underscore image is not defined, and entropy, oh, I just call this ENTR. Let's just do entropy. Okay, and there you go. So it's actually, as you can see on the left hand side and the right hand side where we have a lot of cells, it's showing like pretty bright region, and in the middle it's pretty dark. Now we need to add another step. We need to take this image and process it further to highlight this scratched region. So what do we do now? We can apply a threshold now to segment these two regions. That's pretty much it. So how do we do, and which threshold to apply? There are, again, various options for when it comes to threshold. So one good feature that we have in Scikit-image is from skimage.filters, we can actually import something called try all threshold. Okay, And now let's go ahead and plot this. All of these that actually got thresholded. So figure equals to try all threshold, and let's do entropy. What is our image? Entropy underscore image, and let's do figure size equals 10 and 8. That makes sense. And again, go ahead and read about this on somewhere on Google. It explains exactly what each of these is, and plt.show. And now let's go ahead and show this. So all we're doing is taking this image, the entropy image, and we are calculating threshold based on whatever that try all threshold is. And apparently there is ISO data-based thresholding, Lee thresholding, mean, minimum, OTSU, OTSU. You probably heard of this if you're an image processing expert using prepackaged software. Triangle, which seems to have done a horrible job with our data set, so we definitely are not going to use triangle, not going to use this yen, because again it's not giving me a clean image here. The best ones would be either this minimum or OTSU. Mean also works very well. ISO data also works very well. Let's just pick one of these. Okay, let's just do OTSU based thresholding. So let's also delete this line and keep the code clean. So far, what we have done, literally this is our code. We have done a lot, but the code looks so clean. Imported the right packages, imported our image, and just applied entropy filter. So you can actually see that it filters the image to give us an image that's easy to segment using threshold. We could have never, this was not even possible using the original image right there, because you cannot do thresholding on this image and expect to get a decent result. So in order to get that, we are using the texture of this, using entropy filter, and created an image that is thresholdable, if that's a word. Okay, so now by looking at this, we realize that OTSU is probably a very good way of thresholding this image. So now let's actually get down to how to do this OTSU. And this is in from skimage.filters. Of course, there are numerous filters within skimage.filters. I want to import threshold underscore OTSU. And how do I know it's here? I literally Google searched before this tutorial where to find OTSU. So I just Google searched Skimage and OTSU, and this is where it showed me. So now let's create a thresholded image, and this is nothing but the threshold of our underscore OTSU of entropy image. Okay, and what this does is actually gives us, let's go ahead and run this so we can understand exactly what happens. So if you look here, in fact, we have too many variables. Let me go ahead and clear them and run this again so you can see what the threshold equals to. Threshold is nothing but one single number, which is 2.13 something something. So this is not going to give us, threshold OTSU is not going to give us an image. It's going to give us one value, which corresponds to the threshold for this specific image right here. So now I need to convert this into a binary image just by, I'm going to just call this binary, equals entropy image or entropy image less than or equal to, okay? So all I'm doing is my binary image is equal to a, this is a logical operator, right? So if entropy image is less than or equal to my threshold value, then it is true. If it is greater than or equal to my threshold value, then it is false. That's it. So I'm creating a binary image or a thresholded image where all the dark pixels is true and all the bright pixels is false. That's pretty much it. So when I run this, it should say that my binary image right there is a Boolean type of image that has our array that has false, and there are very few. I mean, if I expand this, you'll see some truths there. That's it. Okay. And now we can go ahead and I am show and let's show binary and cmap equals ay. Okay, so let me go ahead and run this, and now we should see our thresholded image right there. Okay, so 3 or 4 lines of code if you know what you're doing, literally 3 or 4 lines of code, and we can put all these lines in a loop, while loop, for loop, it depends. We can put this in a loop to actually go through all the 5 or 10 images in the time series, and that's it. But just looking at the image is not the essence of microscopy. Quantifying what you're seeing is the essence of any image processing. So let's go ahead and print out the percentage of white pixels, and let's just say the percent bright pixels is, let's say, okay, how do we calculate the percentage of bright pixels? This is nothing but numpy, right? This is a numpy array that we need to sum what of all pixels in binary that are equal to 1. Again, binary false equals to 0, binary true equals to 1. So by the way, it's saying np name is undefined. So let's go back up here and say import numpy as np. Okay, so np binary equals to 1. So this just gives me how many binary pixels I have. I want to get the percent by bright pixels, so I'm going to divide this by same thing plus binary equals to 0. This is or all pixels, you know, instead of binary we can let me keep things simple. Binary equals to that plus binary equals to 0. Okay, and let's multiply the top by 100, so it is a percent. Okay, this is nothing but I may have missed a bracket here, and it will yell at me if that's the case. So this is about 28.9% is the bright pixels right here. So again, all I'm doing is looking at all the pixels that are true, divide by all the pixels, which is true and false. I hope you found this tutorial useful, and let's continue segmentation in our next tutorial. Thank you very much.